To calculate the Reynolds number for a drilling fluid, we must first actually calculate what's called the effective viscosity. And the various models, Bingham Plastic, Power Law, and Herschel-Bulkley, calculate the effective viscosity quite differently. Okay, taking the effective viscosity, which is mu sub E here, for Bingham and Power Law, just as an example. I don't want you to remember these equations. I'm not a great one for trying to use equations to work stuff out, especially if you've got a computer to do it, but it helps to know what goes into the equations so that you can actually work out what your inputs might, what effect your inputs might have, and where sources of errors can come in. So just looking at Bingham, you've got pipe effective viscosity and an annular effective viscosity. We've got YP and PV in here. We've got velocity on the bottom, a geometry value on the top, and constant as well. For Power Law, we've basically got pipe effective viscosity and annular effective viscosity. And here we've got viscosity figures similar to PV and YP, except with Power Law you're talking N's and K's. And you've got velocity and geometry considerations in there. And I mean, it's taking account of the non-Newtonian, how non-Newtonian the fluid is by incorporating all these N for pipe and N for annulus values in here. And it's taking account of geometry as well. As I said, I don't really want you to remember these equations. It's useful to know, it's useful to just have a glance at the equations occasionally to sort of give you an idea of where your inputs are actually being used and what effect some of them might have, how large an effect any errors in them might be as well. Now we'll now examine two of the methods outlined in the Baroid Fluids Handbook to calculate the pressure drop in a simple system. It's Chapter 9. Chapter 9 in the Baroid Fluids Handbook is the hydraulics section. It's worth a read as well. Now these are also mentioned in the original version of API RP13D, as I said, the third edition. And there's a new version of API RP13D that should be out very shortly. Basically, the two versions that were in the Baroid Fluids Handbook, Chapter 9 and API RP13D, I'll talk about here right now. It's easier to talk about these two because they're much simpler equations. Talk about the SPE method for Bingham plastic fluids and the Power Law API method as well. And just go through some of the equations and show you how they're derived and so on, just to give you a feel for what goes into the calculations. Now, calculating the pressure drop using Bingham plastic, well, first of all, you'd have to determine the fluid velocity. There are usually two equations quoted in the literature or in any manual for fluid velocity. Now, you can either have 24.51 times Q divided by the effective diameter squared, and that gives you it in feet per minute. Or more accurately, you've got 0.408 times Q divided by the effective viscosity squared, and that's in feet per second. I'd use this one in preference to that one because this constant is more accurate than that constant. That constant's derived from that one, and it's an approximation, or more of an approximation than this one is. So using this one, that's why I put a little smiley face there. It's just, you'll get a more accurate fluid velocity. You can convert it to feet per minute just by multiplying by 60, obviously. That's what's happened in the constant here, but they've rounded it up. So once you've got your fluid velocity, you have to calculate what's known as the Hedstrom number, which is a bit of a headache as well. And that's using PV and YP, the ID of the pipe. This is the Hedstrom number for pipe. Large constant here in the density of the fluid. The Hedstrom number for the annulus is just another large constant with the effective annular the effective diameter in the annulus squared multiplied by the YP and the density of the fluid divided by the PV squared. So the Hedstrom number is one of these two things for either pipe or annulus. And once you've calculated that, it then refers to this graph, which can be like electronically in the computer's brain, if you like, in the memory of the PC. But you then look at this graph and you read off your Hedstrom number and then find out what the critical Reynolds number would be. And so you can then calculate, we'll then move on to calculate the actual Reynolds number. We know what the critical Reynolds number is based on what this Hedstrom number that we've worked out. And we can tell whether we've broken into turbulence by going beyond that critical Reynolds number. You'll notice that down here, the Hedstrom number down here, we've got basically 2100 going along there, and then it starts to increase. As the Hedstrom number increases, the critical Reynolds number goes up beyond 2100. So then, once you've worked out the critical Reynolds number by looking at that Hedstrom number chart, this is if you were doing it by hand, you would then calculate the actual Reynolds number. And the Reynolds number for pipe is basically its density, fluid velocity, times the ID of the pipe divided by PV, all multiplied by 928 for inside the pipe. Inside the annulus, it's 757 times the density, velocity, ID minus OD, ID of the hole minus the OD of the pipe divided by the PV again. So you've worked out your Reynolds number, and you can compare that to your critical Reynolds number. If the Reynolds number is greater than the critical Reynolds number, then the flow is turbulent. Simple as that. So then, once you've worked out whether it's laminar or turbulent, you now know which equations to apply. And you can have turbulence in the pipe or in the annulus, and you can have laminar flow in the pipe or in the annulus. And the equations are quite different, and you can see what's different about them. What I've just been telling you about the equations earlier when I was talking about what's actually important in turbulence and what's important or what's important for bringing on the onset of turbulence. If we have a look at these equations, we've got density, fluid velocity, and geometry and length. Obviously, the length matters, giving you a pressure in turbulent flow. And the same in the annulus. We've got geometry and we've got velocity. It's almost velocity squared here to the power of 1.75 in the Bingham pressure drop equations. And we've got density expression here. So we've got density, velocity, and geometry, basically. In turbulent flow are the important parameters for pressure. But when you're in laminar flow, the density, velocity, and geometry are less important, but what comes more into play in laminar flow is your viscosity. If you have a look in these equations, we've got PV, we've got PV and YP in both of these equations. And we've still got velocity, but it's not velocity. Here it's velocity to the power of 1.75. It's very nearly velocity squared. Here it's just velocity. So as I was saying, if you double your flow rate, you pretty much quadruple the pressure in the annulus, or well, pretty much the pressure. If you double that flow rate, or double the annular velocity, or the pipe, or the fluid velocity in the pipe, you quadruple the pressure, because it's very nearly a velocity squared equation here. Here, if you double the velocity, you're pretty much going to just double the pressure. That's the sort of relationship. That's the difference between these. You've got more viscosity-related pressure in laminar flow. Density takes over from viscosity when it's in turbulent flow. And again, the pressure increases much more rapidly as the velocity increases in turbulent flow as well. So moving on to the API method for calculating the pressure drop using the power law method. This is the other model that's in the Baroid Handbook, Chapter 9. You have to calculate first the fluid characteristics, N and K. Now, N for pipe is this expression using the 600 and 300 rotational speeds of the fan rheometer, and K for pipe is using 300 rotational speed, and these constants and 511 to the power of N here as well. For the annulus, we've basically got the 100 and the 3 readings. And as I've said before, our software doesn't always use this 103 reading, because you normally, for power law in our software, you just be putting PV and YP in. So you may actually be using the same N and K values for both. But as I said, you're not really wanting to use power law anyway. You'd prefer to use Herschel-Bulkley, as we'll find out. You have to, again, first calculate the fluid velocity. And you'd calculate this for each pipe section and annular section. using this equation, 0.408 times Q flow rate divided by the effective diameter squared. So that could be the annular effective diameter or the internal diameter of the pipe squared. And you could multiply by 60 to get feet per minute as well. And once you know the fluid velocity, you can then put that into these effective viscosity equations. And the effective viscosity equations are basically using you've got geometry, a couple of constants in here, you've got N and K in there. Your N and K values are determining your viscosity. Your effective viscosity is determined by the viscosity terminology and the fluid velocity as well. And same in the annulus, it's just a slightly different equation, but it's basically the same thing is occurring in the annular effective viscosity equation. You're relating the viscosity terms, N and K, to the fluid velocity and the geometry as well. Once you know your effective viscosity, you can then put it into a Reynolds number equation again and work out your Reynolds number. The Reynolds number in the power law method, it's only worked out with one equation, and that's 928 times the effective diameter times the velocity, the fluid velocity, times the density of the fluid divided by, again, the effective viscosity. So you've got geometry, fluid velocity, and density, and counteracting that, we've got the viscosity holding the Reynolds number down, and these ones are increasing the Reynolds number. So the greater the viscosity, lower the Reynolds number, the greater the density, bigger the channel, the faster it flows, the larger the Reynolds number, and the closer to turbulence you get. Now for the critical Reynolds number, to find out whether it's laminar, turbulent, or transitional, the laminar upper boundary is 3470 minus 1370 times N. And the turbulent lower boundary is 4270 minus 1370 times N. And somewhere in between, if the Reynolds number is between these two boundaries, the flow is transitional and it exhibits some of the characteristics of both of the regimes, the laminar and the turbulent regime. And you can see here that that N, or the power law index, basically, of the fluid determines when it transitions from laminar to turbulent flow. So N is on the the power law index here is basically determining at what point the onset of turbulence occurs, or when it leaves the laminar flow regime. It's an important difference between the plastic and pseudoplastic models, so Bingham plastic and pseudoplastic models. It's also pretty much intuitively obvious, I would have thought as well. If N equals 1, then the Reynolds number becomes a straight line. If the Reynolds number, well, basically if N equals 1, it's 3470 minus 1370. And that gives you basically, we've got 2100 as a divergence from laminar to turbulent. And basically you'd end up with, if that was 1, it would be 2900 would be the onset of full turbulence. So somewhere between 2100, if N's 1 here, is when it crosses 2100, it becomes, it's no longer purely laminar. It's now intermediate flow or transitional flow. When it gets to 2900, it's fully turbulent. So, and basically if N reduces from 1 and becomes less of a Newtonian fluid, more of a non-Newtonian fluid, let's say N was 0.1, it's quite a curved profile now in the on your shear rate versus shear stress graph, and making N 0.1, you've got this curve. Basically, things get a little bit stranger because the laminar flow exists until a Reynolds number of now 3,333, and turbulence doesn't actually start until you get to 4,133. So if a fluid's quite non-Newtonian, it behaves significantly differently from a Newtonian fluid. And it's determined by how non-Newtonian it is, which is the N value. So once you know whether it's laminar, turbulent, or intermediate flow, you have to calculate another value called the fanning friction factor. So if Reynolds number is greater than 4270 minus 1370 times n, then the flow is turbulent. So if the flow is turbulent, you use the fanning friction factor equation for turbulent flow, which is this value A divided by Reynolds number to the power of B. And A is log n plus 3.93 divided by 50, and B is 1.75 times log n divided by 7. I'm glad a computer actually does this for you. We used to have to work it out by hand, but not anymore, thankfully. Now, if the Reynolds number that you calculate is between your laminar flow boundary, which is 3470 minus 1370 times n, and your turbulent boundary, which is 4270 minus 1370 times n, then the flow is basically transitional. So you have to work out a transitional fanning friction factor, which is basically an incredibly complicated equation. 16 over Reynolds number, the actual Reynolds number that you've worked out here, plus that same Reynolds number minus your laminar boundary Reynolds number, which is whatever this is, divided by 800, times A divided by your turbulent boundary, which is determined by that, minus 16 over your laminar boundary, which is again determined by this. So it's a reasonably complex bit of algebra here, but you end up with just basically a fanning friction factor for transitional flow, which takes into account, if you look at the equation, it's taking a bit of both worlds into account. If the Reynolds number is less than your laminar boundary, then you use a couple of very simple equations for fanning friction factor for laminar flow. Inside the pipe, you've got 16 over the Reynolds number, and for inside the annulus, it's 24 over the Reynolds number, and that's it, simple as that, for laminar flow. So for laminar flow, your friction factor it's usually going to be laminar in the annulus, and generally it will almost certainly be turbulent within the pipe at normal drilling flow rates. Not always, but that's a fairly decent generalization. You have to use a turbulent friction factor, or certainly an intermediate one for inside the pipe, and in the annulus it will be generally laminar, perhaps intermediate. Now, once you've worked out whatever the fanning friction factor is for each individual section of the wellbore, that's all the internal sections depending on the diameters of them, and all the annular sections, you can then work out the pressure drop over each of these intervals. So you put your fanning friction factor for the interval into this equation, multiply by the square of the velocity, the fluid velocity in that section, and your density is going to be, if you were doing this by hand, you would probably be using a constant mud density, a constant fluid density. If you're using something like DFG, like Baroid's fluid modeling software, this density might be varying depending on your on whereabouts in the well you are, your temperature and so on, as we'll discuss later. Multiply all that by the length of the section, just the section, the annular section or the internal pipe section, divide by a constant, and also divide by the effective diameter, and you get your pressure drop over the interval. And that would be what you would use for power law. And basically, in the end, the equations are the result of research. Some other people have done the research for us. And I'm not actually here to teach you these equations. Our software easily performs these calculations far, far more easily than we can on a calculator. What I'm actually here to try and get across to you is what's actually going on in a fluid when it's flowing and when it's carrying cuttings. And I want you to think of all these principles and ideas whenever you examine a PWD log. And I want you to basically understand why pressure fluctuates within a clean fluid, and then be able to make some decent deductions as to why pressure might be fluctuating within a fluid while it's drilling. So bear with me with all these equations, but they're only there to actually show you where the values that you're putting in within the software actually end up in some of these equations. Now, you'll notice that I haven't gone on to go through all the Herschel-Bulkley equations and so on. That's because there's a fair degree of iteration going on in them, and it just becomes this module would just become a whole load of slides filled with numbers and equations, and I don't really want you to have to remember them. You can easily find out the equations from the literature, and you can look into what goes where and the effects. You can work this sort of thing out for yourself. I don't really expect you to ever have to work out this sort of thing these days by hand. Having them in a tally book or having them written down on a PC, handheld PC, something like that, it wouldn't hurt to have them noted somewhere just so you can refer to them. But I would never expect anyone to be actually remembering all this in their head and going through it on a calculator. So, the equations are there if you want them. I'm really showing you them to show you the effects of viscosity, the effects of geometry, length, density, and velocity, and so on, and where they all fit in, and how the equations are there to show you how they all react together and how they change the flow behavior and the fluid flow regime, basically. Right, some of the things I want you to actually take away from this module, not the equations, some of the principles that I want you to take away from the module. The first one, small changes in pipe diameter have large effects on pressure drop. So if you had a pipe diameter of 5-inch internal diameter and you decreased it by 10% and had 4.5-inch ID, that would result in an increase in frictional pressure drop by about 65% if you run that through some of these equations. I mean, put them in, feel free to plug the values into Insight or into some of these equations, work them out on a calculator. You'll see that the effect of changing the ID by 10% has about a 65% increase in pressure drop through that section. Now, the length of the section also has a great effect on pressure drop. So you can easily see that the length, because the length is in these equations, and you've also got geometry in the equations, if you have a slight error in your ID and then you multiply it by whatever the length of the section is, say in drill pipe where that could be several miles or kilometers long, that's going to have a great effect on the pressure drop as well. And changing the friction factor or the roughness may well affect the flow regime as well. And I'll discuss the roughness later. It's also, you can read about it in the manual, see whether you want to actually use roughness or not, and consider the effects of that. Now, the density of the fluid will also determine the onset of turbulence as much as geometry and velocity do as well. So the geometry and velocity had really determined the onset of turbulence, but the density of the fluid as well. The denser it becomes, the higher the Reynolds number, the quicker it will reach turbulent flow, basically. And if you double the flow rate, the pressure loss in the string quadruples. Now, that's a generalization again, but assuming that string flow is normally turbulent, if you double the flow rate, you're going to quadruple the pressure drop through that string, so your standpipe pressure will rise much more quickly. And these are some of the things I just want you to take away from having looked at these equations. And if you plug a figure in, you'll be able to work out the effects on the answer that you're going to get based on some of these notes. So you're now able to describe the difference between laminar and turbulent flow. You should be able to relate these descriptions to flow of drilling fluid through varying geometry and also varying fluid parameters. And you should understand the significance of the Reynolds number and how the Reynolds numbers relate to flow regimes, laminar, intermediate, or turbulent. And you should be able to consider the effect of a flow regime on the well being drilled, such as turbulent flow has an ability to erode the well. Laminar flow will be slower in general than turbulent flow, therefore it might have the same carrying capacity, things like that.